Hello, chemistry students. Dr. Tullis here. In this section, we will assess nuclear stability based on the numbers of neutrons and protons in a nucleus and predict possible modes of decay of unstable nuclei based on the neutron-proton ratios. We're going to look a little deeper at why some isotopes are radioactive and some are stable. Let's look at this figure. We can learn something about nuclear stability from this. This is a plot of the composition of the known isotopes of the elements. The horizontal axis represents the number of protons, and the vertical axis represents the number of neutrons. Each circle represents an isotope identified by the number of neutrons and protons contained in its nucleus. The black circles represent stable isotopes or non-radioactive isotopes, and the red circles represent some of the known radioactive isotopes. There are 254 non-radioactive isotopes. For example, there are 3 isotopes of hydrogen in this very first 3 dots down here. Hydrogen 1 and hydrogen 2 are both black dots, the very first 2 black dots. They are both stable, but hydrogen 3 is radioactive. For lithium, the third element, there are 4 isotopes, lithium 4, 5, 6, and 7. The isotopes with masses of 6 and 7, which are black, are stable, but the other 2 isotopes that are in red are radioactive. Stable isotopes fall in a very narrow range called the band of stability. It's remarkable how few isotopes are actually stable. Only hydrogen 1 and helium 3 have more protons than neutrons. Up to calcium, that has a proton count of 20. Stable isotopes often have the same number of neutrons and protons. But beyond calcium, the ratio of neutrons to protons is greater than that 1-to-1. As protons increase, the neutron to proton ratio deviates further from 1-to-1. Above bismuth, who has 83 protons and about 126 neutrons, all isotopes are unstable and radioactive. The forces of attraction between nuclear particles are not strong enough to hold heavy nuclei together. Isotopes that fall further from the band of stability tend to have shorter half-lives than do unstable isotopes closer to the band of stability. Above calcium, elements that have even atomic numbers and even mass numbers are more stable than isotopes that have odd atomic numbers and odd mass numbers. All elements beyond bismuth, so an atomic number of 83, are unstable. Alpha emission helps decrease the atomic number to reach the band of stability. So alpha emission is most common for elements beyond bismuth. So americium, for example, has an atomic number of 95. It's unstable. So it's going to undergo alpha emission, giving us an atomic number of 93, which is NP. Again, we take our 243 and we minus 4 to get that mass of 239. Beta emission is probably going to occur for isotopes that have a high neutron to proton ratio, so isotopes above the band of stability. Remember that beta emission increases the number of protons. If I have cobalt, atomic number 27, and it undergoes beta emission, that means I'm going to have nickel, which has a proton count of 28, and the mass number stays the same. If we look at that neutron to proton ratio for this cobalt, if its mass is 60 and its proton count is 27, 60 minus 27 gives me a neutron count of 32 to a proton count of 27. So that's a pretty high, it's greater than a 1-to-1 neutron to proton ratio. Isotopes that have a low neutron to proton ratio, below the band of stability decay by positron emission or electron capture. Here's a couple examples. If I looked at the neutron to proton ratio for this nitrogen isotope, it would be 6 neutrons and 7 protons. And for this calcium, it would be 21 and 20, so lower, close to that 1-to-1 ratio. Here's an example of a positron. Here's an example of electron capture. Both of those reduce the atomic number. Positron emission means I'm going to go from 7 to 6, and my mass stays the same. Notice it's 13 here and 13 here. That's positron. Electron capture, notice I go from 20 to 19, and 41 and 41, same mass. Here's just another graphic I found showing that towards the bottom are the lighter isotopes like hydrogen, helium, and carbon. And towards the top are the heavier isotopes, thorium, uranium, plutonium. And in that region there are no stable isotopes. They are all experiencing radioactive decay. So when it comes to predicting the modes of radioactive decay, if the proton count is greater than 83, alpha decay is likely. Then you want to look at the neutron to proton ratio. If the ratio is much greater than 1, beta decay is probable. If it's less than 1, then positron emission or electron capture is the more likely process. Let's look at the probable modes of decay for each of these isotopes. Why don't you take a minute and predict what would happen? For this first one, I looked at the neutron to proton ratio. So 15 minus 8 gave me a neutron count of 7, and obviously protons is 8. So it's less than the 1-to-1 ratio. It would either be a positron or electron capture. Here's how positron would look, giving me nitrogen 15. If I did electron capture and I had my 0 and -1 E on the left, I would have the same product, this nitrogen 15. This uranium has an atomic number greater than bismuth, greater than 83, so most likely alpha decay is going to occur. So if I have 92 on the left and alpha decay is occurring, that means my other element that it's decaying to is 90. 234 was the mass. 4 of that is alpha, so this mass of thorium will be 230. Fluorine 20, so if it has a mass of 20, 20 minus 9 gives me a neutron count of 11. So 11 neutrons to 9 protons. That's a high neutron to proton ratio. So beta emission is most likely, leaving me with neon 20, which is a much more neutron to proton 1-to-1 ratio. This manganese 56 isotope, it's suggested that it's radioactive because it has a high neutron to proton ratio. So beta decay is most likely for this mode of decay, which would give me iron 56. Pause the video here and write an equation for the probable mode of decay for each of the following unstable isotopes, and write the equation for that nuclear reaction. For silicon 32, we've got an 18 to 14 neutron to proton ratio. That's a high neutron to proton ratio. It's above the band of stability. With beta decay, that is probably the most probable mode of decay for this reaction, giving us phosphorus 32. In the case of titanium 45, we have a lower neutron to proton ratio, so the decay by positron emission or by electron capture is the most probable form of decay. For plutonium 239, we have an atomic number above bismuth, so alpha decay is most likely. And for potassium 42, our neutron to proton count is high, so we were probably looking at beta decay. I have 4 practice problems. Pause the video here to see if you can answer the third step of this equation. Well, for the first step, we were told it was alpha decay. I started with uranium 235. Alpha decay means that on the right, I have 4 over 2. So that means on the right, I need 231 and 90. That then becomes my starting point for the second step, which is beta decay. Beta decay on the right, if I have a -1, that means this needs to be 91. If I look at the periodic table, that's Pa, and the mass stays the same at that 231. So this then becomes the starting point for my third step, and the only option here would be this last guy. And it does say that it's followed by alpha decay. Alpha decay over here, so therefore 89 plus 2 would be 91, and 227 plus 4 would get the 231. Pause the video here. Of these 4 options, the highest neutron to proton count would be the hydrogen and the fluorine. Those are the ones most likely to decay by beta emission. Pause here. Hopefully you said alpha decay. It has a very large atomic number, higher than bismuth, so alpha is most probable. Pause here. It has a pretty high neutron to proton count ratio, so beta emission is most probable.